Hello people, my name is Nosratullah and we're here to present you the effect of engagement on response. This presentation is part of the project that we had in Nueromatch Academy in 2020. Our mentor is Benjamin Tan, and here you can see the name of the team members: Ramya, Nosratullah, Michael, Lindy, and Arsena. The problem that we studied and focused on is that how does the mouse's engagement level affect the response? The scientific background is the stimuli that drive actions during an engaged behavioral state do not necessarily drive actions when disengaged. It remains unclear whether this context-dependent gating occurs globally or whether it involves multiple brain systems differentially. The dataset we use is StainNets, which is a huge dataset of neural pixel information of 10 mice captured while performing a go, no-go task with visual stimuli. Across all the trials, data has been recorded from 30,000 neurons from 42 brain regions and from 10 mice in 39 sessions and about 9,500 trials. Due to the simplicity and the short time we have, we only choose one mouse, one session, at up to 350 trials, and each trial must consist of 700 neurons from 42 brain regions. The dataset provides information to analyze the vision, choice, action, and behavioral engagement of the mice. To investigate our problem statement, we analyze the engagement of the mouse and study its relation to the visual stimuli, choice, and action taken by it. Here, pre-stimulus activity describes the engagement level of the mouse. And using this pre-stimulus activity, we analyze whether different areas of the mouse brain behaving differently before stimulus onset help us predict the choice and action taken by the mouse. Here you can see the terminology that the dataset provides for us.
Hi, I'm Ramya. I'm going to walk you through how we studied our hypothesis. The graphs that you see here are examples of single neuron activity. This 2.5 seconds is one trial. So the green one indicates that during the trial, the green line indicates that this is the time when the stimulus was shown. The yellow line indicates the time when the go cue was sounded for the mouse to start moving. And red is when the response has been recorded. In these graphs, you will see that the first graph is an average pre-stimulus activity across all the brain regions and across all the neurons. We cannot visually interpret this average brain activity. It's not really telling us anything about the difference between the correct trials, wrong trials, missed trials, or passive trials, with respect to the pre-stimulus activity. Let's move on further. And when we're moving on further, we'll now consider our plots in four different brain regions. We'll average across all the neurons in those particular regions. So it's not really a mash of all neurons across all brain regions. So the four brain regions we look at are visual cortex, thalamus, hippocampus, and other cortical areas. So in this graph, in the second graph, we see how pre-stimulus activity determines or does not determine mistrial and passive trials. And unlike the previous graph, in this graph, we can clearly visually interpret of neurons in the visual cortex. The interesting part about this is, despite passive and mistrials having the same input of visual contrast, visual stimuli, and having the same output of standing still and not the desired output of standing still and not moving, they have different brain activity that is going on in brain regions. Moving on to the go and miss trials. In this, again, we see that the graphs are very interpretable. That is, the pre-stimulus activity can easily determine, that is, we can see that the graph fluctuates so much, and some of the in the visual cortex and in the other cortical areas, the pre-stimulus activity of mistrials is very high, and the pre-stimulus activity of mistrials also fluctuates a lot, and this makes it very interpretable. And even a human, the test accuracy, so I thought of fitting it into a logistic regression and seeing if I can accurately predict the binary response of, a mistrial or a go trial using pre-stimulus activity, and lo and behold, it gives, we can predict with an accuracy of 94%. Go and mistrials is when the mouse, we have given the cue for the mouse to move, and the mouse is to decide, make a choice whether it wants to stay or it wants to move. It wants to stand still or it wants to move. So this is the choice. We have seen that we can accurately determine it. Now, correct and wrong trials. Now, given the pre-stimulus activity, can we say if the mouse will make a right decision or a wrong decision? So again, looking at the graphs, it's interpretable when you do a binary classification of a correct movement or a wrong movement trial. With 95% accuracy, you can predict that. Hence, prove that, hence it's shown that we can also predict whether the mouse is going to take a right decision or a wrong decision. Coming to contralateral or ipsilateral actions, so the neuropixels have been recorded from the left hemisphere. So the contralateral hemisphere would be your right stimulus, right responses, and your ipsilateral would be your left responses. So what we wanted to see is, can we predict the direction in which the mouse will move its wheel depending on the pre-stimulus activity? And it turns out we cannot. First of all, the graphs are not visually interpretable. However, we tried even logistic regression, and even that failed, and it's worse than random. Actually, it's just 43%. So we realized that despite the mouse predicting, despite pre-stimulus activity predicting accurately the choice and the right or the wrong, it cannot predict the action. So coming to our conclusions here, there are clear observable differences between go mistrials and correct wrong. Engagement can accurately predict choice but not action. Learn that greater the pre-stimulus activity doesn't really translate into greater accuracy, because greater pre-stimulus activity led to mistrials and wrong movements. So it turns out you have to apply proper classification models. Also, we see from these trials that having a calm mind with not too much fluctuations in your activity, in your pre-stimulus activity, results in better task response. This analysis, as I mentioned earlier, is only done on one session of one mouse. And we want to corroborate this further with more sessions of the same mouse and compare that with other average sessions of other 10 mice. Coming to the learning experiences of this project, we learned how to work with neuropixel information and how to interpret the data set and all the terminology. Learned how to read like a neuroscience experiment paper. It was so exciting. We read this paper and we enjoyed it so much. We also came up with our own interesting hypotheses, and we checked it ourselves, heavily taking help of the paper, of course, and learned how to apply correlation, regression, and plot in an informative manner, and also work in a manner that supports, or that make all our plots and everything try around that hypothesis and wanting to study that one question so that we're not distracted. That was also an interesting experience. Okay, that's it. Thank you so much for holding this Nueromatch summer school. I learned a lot, and especially from India, we do not get such opportunities always. I mean, most of the time, so we do not get these opportunities. So I'm really, really grateful, and I learned a lot. Thank you so much. Have a great year ahead.